Okay guys, in this video we're going to revise how to do definite integrals. Now these are very similar to doing the indefinite integrals, which is just finding the antiderivative, except in this case you're then substituting values in to evaluate that integral. Now you can tell something is a definite integral by having terminals. These A's and B's are called terminals of integration, are sitting on the integrand symbol. And a very common use of this is to find the area under a curve or between curves, but not always. Often it's just evaluate this particular value. Now we use this rule, this equation here. It's called the fundamental theorem of integral calculus. You don't have to know that, but that's what it's called. And essentially what it's telling you to do is anti-differentiate f of x, that's lowercase f, and becomes uppercase f. Remember in the previous video about integration rules, the antiderivative of a lowercase f by notation is capital F. So we anti-differentiate and then we substitute b in and then substitute a in and find the difference. So let's do that. Oh, a couple other rules, by the way. We flip, if we change the a and b around, flip those around, we put a negative at the front. And I can break up A to B into two parts, so A to C plus C to B. As long as C is between them, I can split this integral up into two parts, which is really important. So let's evaluate all these ones. Let's start with something nice and simple. So we have x plus 5. When I anti-differentiate x, that becomes x squared over 2. Plus 5, that becomes plus 5x between 2 and 4. And then we substitute 4 in, so you get 4 squared over 2 plus 5 times 4. And we put 2 in, so 2 squared over 2 plus 5 times by 2. Now, we're told to subtract, which means we'll be very careful and put brackets around the second part, otherwise we're going to make errors. So you get 4 squared, which is 16, divided by 2 is 8. 5 times 4 is 20, minus 2 squared is 4, divided by 2 is 2. 5 times 2 is 10. So notice now I've expanded this out and subtracted the 2 and the 10. So the negatives come from. And then we finish it off by doing 20 minus 10 is 10, plus 8 is 18, and it was 16. Now, if there's no area applied to it, 16 is sufficient. But if you have an area, you should write something like 16 units squared, or whatever the unit they've given you is, if they've given you one. So let's do this first, this next one, this cosine. Now we need to remember the antiderivative of cosine is sine. So this 2 stays there, and you end up with sine of 2x. And don't forget that this factor, this 1 over 2, comes out the front here. We close our brackets, we put a 0 and a pi, and we substitute in. So we get 2 times a half, of course, is 1, so we end up with sine of 2 pi minus sine of 0. Now I have more brackets in this case because there's only one term. If you've got 2 terms, you need brackets. 1 term, not so much. Now sine of 2 pi happens to be 0, as does sine of 0. So in this case, 0 minus 0 gives you 0. Now if I was asked to find the area between this curve and the axes, that would be a problem because we know a cosine graph does that. So I can see there's area happening here, but because there's no application to area, that doesn't matter. Last couple. This next one, we've got 2x plus 1 to the power of minus 1. That indicates it's a logarithm. Remember, our rule does not work with -1. I can't increase that power by 1, which would be 0. I couldn't do this and then divide by that new power because I'm dividing by 0. So anytime you have a power of -1, it must be a logarithm. So we end up with logarithm of 2x plus 1. But we also have a factor of 1/2 comes out the front. It's always 1 over the coefficient of x. And that now happens between 1 and 5. Substitute our values in. 2 times 5 plus 1. Oops, too early. Goes there. Minus 1/2 2 times 1 plus 1, and we can simplify. So 2 times 5 is 10, plus 1 is 11, minus 1/2. 2 times 1 is 2, plus 1 is 3. And to finish it off, you would have 1/2 log base of e of 11 over 3. You couldn't leave it like this because you've got 2 logs with the same base. Therefore, you can combine them. And because you've got the same factor at the front here, you're able to use your log law. Got to make sure the factor at the front is the same to use your log law in this way. Last one. We got 3x plus 2 to the power of 2. Well, this one does not have a power of -1, so I can just go 3x plus 2 to the power of, increase that power by 1 and divide it by that power of 3. But we also have to divide it by this 3, because in the derivative that 3 would come out multiplying at the front. So I'm going to multiply it by 3 like that. And then I'm going to substitute e and 0 in. So putting e in, you're going to get 3e plus 2 cubed over 9 minus 0 goes in. You get, I should say, 3 times 0 plus 2 cubed also over 9. And then we're going to simplify 3e plus 2 cubed minus 2 cubed all over 9. This can actually be factorized further. I think on an exam this would be sufficient. Sorry, I have to write that as 8. This will be sufficient on an exam, I would imagine, but you can actually factorize this further if you use the rule a cubed minus b cubed. So in this case, a plus b, a squared minus ab plus b squared. You can actually simplify this further. So we're going to have, that is a minus in this case, sorry. That minus makes that a minus there and a plus there. So what we're going to do, you have 3a plus 2, that's your a. B is going to be 2, so minus 2. And then you're going to have in here a squared, so 3e squared plus 3e plus 2 by 2 plus 2 squared, all over 9. And then we simplify from there. 2 minus 2 is 0, so you end up with 3e coming out the front. 9e squared. 2 times 3e is 6e. 2 squared is 4. And another 2 times 2 is another 4, so it's plus 8, all over 9. I imagine that will be sufficient here, but it's also useful to be able to factorize because it could very well come up. And that is how you use definite integrals.